Microphone testing. 1, 2, 3, 4. 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 Okay, welcome to today's machine learning class at National Taiwan University. Some of you may have watched the course introduction video that I uploaded yesterday in the very last minute. I'm sorry about that. And if you haven't, no worries. Okay, you can watch that part of the video after this live class and decide whether to take this class or not. And for now, we're going to just start with the basics of machine learning. Okay, so if you haven't decided whether to take this class, you may as well just try to go with us through the lecture for you to make the decision. And if you have watched the introduction video and have some questions, please feel free to post them at Slido, and we will answer it in our next Q&A part. Okay, before we start everything, let me quickly check Slido first, okay, to basically help you understand our teaching style here. From time to time, we will stop by Slido to check people's questions. We will possibly not be able to answer all the questions during our live session because currently we have more than 400 students in this class. Okay, but we will try to pick some important ones to answer live. And for other questions, I will actually answer them offline. Okay, so our tradition starting last year was that after each class, I will gather the questions from Slido and provide quick answers to them in a shared document and post the document in the class forum. I hope that this is the best way to ensure that every question you raise on Slido will be answered. Of course, every question, okay, not those funny jokes and things like that. Okay, so let me go to Slido here. Okay, and as you see on Slido, we will occasionally have some polls. Okay, so basically trying to understand like how many people we have online right now. Currently, we have around 200 here, and people express their feelings and things. Okay, and Q&A. Okay, let me go to the Q&A part just to be clear. And okay, there are questions. Okay, and basically, I'm not sure whether this link provided is the live link that we have or not. Sorry for the confusion. But basically what we have here, there's a live cast, and there are some pre-recorded parts that I released yesterday. Okay, those are the two videos that you should watch this week. And where to download the lecture slides? We will upload the lecture slides to NTU Cool. And if you cannot access NTU Cool today, I'm sorry about that. There seems to be a synchronization problem. And we will try to check that or provide alternative ways to download the slides later. Okay, should the questions be written in English? Okay, that's a very good one. Actually, if you have watched the video yesterday, we explained that. Okay, you can ask questions on Slido in English or traditional Chinese or simplified Chinese. I will translate the questions to English before answering. Okay, and okay, I don't think I saw many other important questions here. So we will start the lecture first. Okay, lectures. Let me switch to my lecture teaching part. Okay, so this course is about machine learning, and we are going to start with the very basics, okay, trying to help you understand what machine learning is and so on. And the first topic that we will cover with possibly 2 or 3 weeks is when can machine learn? Basically talking about when we can use machine learning, where the applications are, and so on. And as you can see, we have actually prepared lots of mini topics here today. And to talk about machine learning, let's first think, okay, what we mean by learning. Okay, in our own experience, how can we define the term learning? Well, if you think about that, okay, starting when we were a baby, we started learning. And by learning, we learn actually a lot of different kind of skills. Okay, we learn to, for example, speak. We learn to read. We learn to run, and so on. Okay, and how did we learn that? Well, to get those skills to be somewhat successful or matured or well experienced in those skills, we receive observations. Okay, observations, basically we may observe the environment, for example, with our eyes or ears and so on. We may receive feedback from our teachers, from our parents, and so on. Okay. So if we think about that, okay, we are accumulating skills or accumulating experience through those observations. And through a somewhat internalized process in our brain, that becomes our skill. Okay, we, for example, hear how other people speak. And then we learn how to speak. Of course, we may receive feedback like, okay, how do we say this term? How do we say that term? And so on. And all those observations, okay, I'm using observation in a very general meanings here. It's not just eye sensing or ear sensing or whatever. Observations actually mean all kinds of feedback that we can receive from the environment. And with all those observations, we get our skill. And that's learning. For machine learning, we're simply doing the same thing, okay, except the brain part is replaced with a machine. And in a machine, we call those thinking or experience accumulating process the computing. Okay, so basically we're computing all kinds of things that we receive, and after the computation, we get some sort of skill. And on machines, there's a fancy term for observations. We call them data. That's the difference. Okay, data corresponds to the observations that we receive from the environment, and now we want the machine as a subject, okay, to learn, to get some sort of skill. Now you'll ask, okay, this sounds a little bit abstract. So what do you mean by skill, actually? So again, let's think when we grow, how do we define that we learn some kind of skill? And one way to define that is a skill actually means you improve some sort of performance measure. Okay, so for example, in terms of speaking, okay, if you speak better, you can speak more words and so on, then we say you learn the speaking skill. Okay, if you learn to ride a bike, okay, and basically now you get more stable or be able to ride faster, then we say you learn the skill of biking. And of course, okay, in terms of math, or maybe any computer science subject like machine learning or data structure or whatever, okay, and if you can do better in your homework or your exams, okay, we say you learn the skill of data structure or machine learning or whatever math and so whatever subject. So that's the definition, okay. Skill, you can imagine skill coming with some sort of performance measure that we want to improve. And with this new definition, we can say machine learning actually wants to use data to improve some sort of performance measure. One example that is easier for you to digest is that an application in computational finance, where we actually have lots of data. Okay, we have 10s, 20s of years of stock data there. We can use machine learning to analyze those data and trying to find patterns on whether the stock market would go up or down. And then we hope the machine learns the skill of investment. How do we measure that skill? Well, if, okay, we actually give the machine the money and put it to the market with the investment strategy, we hope that the machine can get more investment gain. And that's the performance measure that we can use to see if the machine is successful in computational finance or not. Okay, so now we have a basic understanding of machine learning, and you see these 3 steps that would recur repeatedly throughout the lecture here. Machine learning starts from data, the observations, and the ending goal is to have some skill that we can measure whether there's an improvement or not. Now you will ask, okay, so I know what machine learning is now. Why do we use machine learning? Well, that's something I want to ask you back. Okay, let's think about another application that we may have. And this, in the picture, what's that? Okay, I assume everyone here would know that there's a tree in the picture. Of course, there's sky and everything, but maybe you'll recognize the tree first. Well, the answer is not always that in computer science, because in computer science, many students believe trees should be rooted at the top, not at the bottom. Okay, so when they see leaves at the top, not at the bottom, they question whether it's an actual tree or not. Okay, but this is a biological tree. Okay, at least that's what we're going to use here. Now my next question is, okay, how many lines of code do you need to write down a program that recognizes trees? If you think about that, okay, to do a decent programming to recognize trees, you actually need maybe hundreds, thousands, or even more lines of code, because to do that, you need to define rules. Okay, rules that describes the tree. For example, leaves are generally green or sometimes yellow in fall and so on. You need to have rules that recognize the branches or trunks or roots or whatever. And if you define all those rules that help you describe the tree and then program it into your machine, it can be difficult. You require lots and lots of lines of code. But if you ask a 3-year-old, okay, what's a tree? Can you recognize a tree and so on? A 3-year-old can typically recognize a tree pretty well through observing the environment, through observing and through getting feedback from the parents and so on. A 3-year-old can internalize a model in the brain, not by rules, okay, but just by thinking and getting a description of the tree. That's, okay, basically a classifier tries to classify whether there's a tree there or not. So in this sense, it may seem easier, okay, to give the machine or any learning subject, okay, lots of data about the trees, ask the machine to learn the representation, learn the rules or whatever by themselves, rather than us coding for them. And that's basically the purpose of machine learning. Okay, nowadays, a machine learning based tree recognition system can be easier to build than hand program system. Okay. Traditionally, if you are turned into maybe 30 years ago or something, when machine learning is not that mature, to build a tree recognition system or maybe a digit recognition system or other such systems, it requires lots of hand programming to use human knowledge to extract the representations, the rules, and so on. Now it's easier to just feed the machines with data and ask the machine, okay, to get the model by itself. Of course, if you know machine learning, that's a big if, okay, but let's just have this dream in mind for now. So machine learning can be thought as an alternative route to build complicated systems. Okay. Complicated systems, hand programming, hard. Okay. Using machine learning, if you know how to do that, easy. And that's the purpose of this class. So there are some use scenarios, okay? And basically the typical use scenarios of machine learning is when humans cannot easily do better. For example, okay, there are cases where machines really need to use exploration on their own and work more dynamically instead of relying on humans to program the system as a whole manually. Okay, for example, when the machine is visiting an unknown environment, okay, we may provide the machines with some principles about what to do, but after all, the machines need to learn to adapt in those environments. And there are cases, okay, for example, the recognition cases that we talked about, when humans cannot define the solutions easily. Okay, for example, visual recognition, right? Okay, if you want to define how to extract the leaf part, how to extract the branch part, and so on of the tree, it can be difficult. Okay, but if you have a proper machine learning model, it can be easier. And there are cases where the human brains are just not defined for that, okay, not designed for that. For example, you may heard of high frequency trading, where in computational finance, the trading happens in minutes or even seconds. And in those cases, okay, the human brains simply do not have enough information to make the decision, while machines can use their huge computation power to counter that. And in that cases, machine learning would be more useful than maybe human brains. And another case is to deal with massive scale applications like internet applications, okay, where the application is serving maybe millions of people. And so again, human brains are not designed for that, and machines can be more helpful, okay, like consumer targeted marketing. And some of you may know, I actually joined a company a few years ago specializing in consumer targeted marketing. We successfully applied many machine learning techniques to that field. So we're just like teaching computers how to fish. Okay, we're not just guiding it to follow the rules that we provide. Okay, but we give machines data and tell the machines to extract patterns from the data to perform better in the particular task. Now, with this very quick introduction of machine learning, okay, I'm ready to tell you some key essence of machine learning, and the purpose of this key essence is to help you understand when to use machine learning or not. Okay, one important thing, machine learning is not always useful. And I'm going to be super honest with you, okay? It is not like, okay, you know machine learning and you can apply it on every problem you face in the future. No, it just doesn't happen. There are tasks that are more suitable for machine learning, and for those tasks, okay, you can consider using them. And there are tasks that are just not suited for machine learning, at least not suited now. And you should double think, okay, before you decide whether to use machine learning or not. And there are three criteria that I often tell people who want to use machine learning in their applications. For one, to use machine learning, you need to have performance measure that can be improved. If you cannot think about a proper performance measure, then you probably should not use machine learning. And generally, to think about a proper performance measure, it actually means you need to assume some patterns of the problem. If there are no patterns, okay, for example, let's say you want to use machine learning to predict, okay, a random coin flip or the lottery number tomorrow or whatever. You probably can imagine that there's really, or there shouldn't be, okay, any underlying patterns in that problem if you believe natural randomness and so on. And if there's no pattern, basically for whatever machine learning model you derive, okay, it will be just equal to random guess. You just cannot improve the performance measure. So if you want to expect an improved performance measure, okay, if you want the machine to learn some skill, you actually need to believe, okay, that the problem is what we call learnable in some sense. Okay, and if you doubt yourself that, okay, this problem is just too hard for any reasonable learning subject, or this problem may not contain any reasonable pattern at all, then you should stop here. You should not use machine learning. Okay, machine learning cannot be successful on a problem that is very likely of no pattern, simply because the machines won't find any opportunity to improve the performance measure. Number 2, when there's a pattern, sometimes the pattern is easy. Easy actually means humans can easily extract them and program them by humans. If you can easily extract them and program them with a few hundred lines of code, then probably you don't need machine learning, because the 100 lines of code is easier than writing another 100 lines of code for the machines and tune them towards the specific problem. So if there's an easy definition, I will not use machine learning. Okay, I will just follow the definition and then write down the definition by myself. Okay, so if there's a pattern but no easy definition, the third criteria that you should check is whether there's enough data. Enough meaning sufficient quality and quantity. Machine learning needs data to learn. If you cannot gather enough data for your problem, then most likely your machine learning route will be doomed. Therefore, if there's no enough data, then you cannot rely on machine learning, period. Okay, so the 3 criteria: existing some patterns, you want to assume or really think about that on your problem first, and also think about whether there's easy definition. If the answer is yes for the first part and no for the second part, then you check whether there's enough data for the problem. And if the 3 criteria are all satisfied, you can consider using machine learning for your task. Of course, there are also other tools as well, but I'm hoping in this very beginning to use these 3 criteria to help many of you, okay, who are not in computer science but in other fields, to decide whether machine learning would help your problem of interest in your field or not. That's the very first part of the lecture here, and basically what we generally do in this form of teaching is that after a few slides, okay, 5 or 6 slides, we will have this little question slide here, and that hints us to switch to Slido, and I'll try to answer some of the questions here before we get back to teach the next part. You are very welcome to ask questions, keep asking questions through Slido, and as I mentioned, basically I'll answer selective questions on Slido live and other questions offline, okay, after the class. Let's switch to Q&A here. Okay, and I'm going to use this popular question mode, and basically to help me select the questions to answer. And you are very welcome to vote for your favorite question to help us with that. Okay, the first question here is asked in Chinese, but I'm going to translate here, is whether the course video would stay there. And the short answer is yes. Okay, basically, as you see, we're using YouTube for broadcasting our course here, and by using YouTube, actually the video would stay in YouTube as well. After the class, we will put the YouTube link, okay, which is not public actually, okay, but we set it to the protected permission after the class, and we upload the protected link to NTU Cool. And so people who have not followed us in the class can continue to watch those. Okay, recorded and uploaded later. That's a repeated question here. And lecture PowerPoint slides before the class starts. Okay, so this question is, for future, will it be possible to access the lecture slides before the class starts? Yes, certainly. Okay, actually, this is the very first week, so there are a couple of pages, okay, that are not there yet. Okay, but I'll try to upload the draft slides to NTU Cool before the lecture begins. Okay, here's a very interesting question. I'm going to translate it here. Does the chatbot have an underlying pattern or performance measure? That's a very good question. And the short answer is, okay, first, it depends on your belief. Okay, if you are designing a chatbot that's simply to give you some answer, maybe you don't need a pattern. Okay? But if you're designing a chatbot that's for human satisfaction, then maybe there's a common sense about how human feels the chatbot, for example, to be human-like or not, or to be helpful or not for the particular task. And in that kind of particular task, there's a performance measure. I'm going to hint here that the performance measure here does not necessarily need to be computable performance measure. Of course, in machine learning, we need to translate whatever performance measure that we have in mind to computable performance measure as much as possible. But it doesn't mean we can only evaluate machines through those measures. We can have measures as a procedure. Okay, for example, we recruit 20 human beings and decide whether the bot is more satisfying or not in the human common sense. Okay, that's a performance measure as well. As long as we believe the problem is improvable, okay, with respect to that procedure, through some patterns that we can observe from the data, we can possibly consider machine learning. What's the definition or meaning of the pattern in machine learning? That's actually a very good question, and we're deliberately keeping this part vague for now. Because essentially, as you will see later, different machine learning algorithms or different machine learning models are actually designed to capture different kinds of patterns. Okay, so it is not like we can have a very simple definition of pattern here. In some models, for example, for time series models, okay, being periodic is perhaps a very important pattern that we want a machine learning model to capture. For some of the financial models, being monotonic, okay, in some parts is possibly a pattern that we want the machine to capture, and so on. So pattern is really part of the machine learning model design. And we will see through the many models that we will teach in this class, different kinds of patterns that people have considered in machine learning. Okay, and there's a comment here that I forgot to use BCC when I sent an email earlier to the class. And I truly apologize for that. Actually, I was trying to send that email in a super rush this morning, okay, when I realized that many of you do not know how to access our live cast today, and I forget that. I'm very, very sorry about that. And I'll try to be more careful next time. I wish I can take that back, but as you know, this may not be possible, but I'll try to be much more careful next time. Okay, thank you for all those questions. I hope you enjoyed this very first part here. Now let us switch to the second part of the lecture, where we will try to understand more about machine learning. Now, let's see some more applications, okay, really to stimulate our appetite on machine learning, and also trying to help you understand a little bit more about what we mean by data and skill and the role that machine plays. One particular application, and this is a newly added application to our slides this year, if you have watched other versions of machine learning that we provided, is in the area of medicine. I'm going to use a problem in computer-assisted diagnosis, where the skill that we want the machine to learn is a dialogue system. Actually, this echoes what another student was asking in chatbot, whether there's a performance measure or not. And here we had the performance measure. We have a special dialogue system in mind that we want the system to efficiently identify the disease of patients. I'm highlighting efficiently here, okay, which means, okay, if you think about what your doctor does when you visit the hospital, your doctor tries to ask you a few key questions before the doctor decides with a high accuracy what disease you may have. So you want the doctors to be efficient. You don't want the doctors to ask you 100 or 200 questions on every possible symptom before saying, hey, okay, this is the particular disease that you have. You want the doctors to zoom in with 3 or 5 questions and then accurately predicts the disease that you have. So there's efficiency, there's accuracy, and those are the performance criteria that we want the machines to perform well on. And what's the data that we have? Okay, we have patient data, maybe gathered from the hospital or simulated data or whatever. And in those patient data, we have the status, the symptoms of the patient and past diagnosis from the doctors. We want the machine to use the data to really learn an efficient dialogue system that accurately predicts the status of the disease of the patient. And this particular work was my student's earlier work as an intern at HTC DeepQ. And we actually had a top conference paper on that, about how to make machines more efficient while being accurate on identifying the diseases of the patient. Second application, communication. And in this communication application, what we want the machines to do, okay, you now have basically many base stations for your communication needs, whether for 4G or for wireless or whatever. And in those base stations, there are configurations, okay, configurations like how you do the coding of the wireless channel, so the communication speed can be as fast as possible. Okay, so again, there's a measure criteria. The measure criteria is perhaps the communication speed, okay, the speed that you enjoy with your wireless network and so on, okay? But it really depends on lots of factors, right? Your the distance to the base station, the interference from other base stations, and so on, okay? And what we want the machine to do is really to use, okay, some information, some data that it has gathered before or it has on hand to decide the best configuration. So the data that we have may have the channel information, how do we do the coding and so on, the configuration, and the data received, okay, basically the quality of the data received. And with this, we want the machine to learn the skill. And this is another work of my student as an intern at MediaTek a few years ago. And this particular 2 cases show the application opportunity of machine learning in very different areas. Okay, one in medicine, one in communication, arguably an electrical engineering area. And there are applications in manufacturing as well. Okay, for example, as you can think, okay, in factories, okay, you need to detect faulty products. Okay, so one of the products we can consider here is this PC board, okay, that you use in every of your electronic devices. And for this fault detection, what we want the machine to do is really to predict which PC boards are faulty. Okay? And the data that we have, there may be PC board images of normal and abnormal ones in the past. Okay, we can give them to the machines and also human mark faulty locations. with those data, we want the machine to learn to predict the faulty PC boards. And of course, we can measure by false positive, false negative, and so on. And this is a very important ongoing research direction for smart factory, not just for PC boards, okay, but basically for all kinds of products that we manufacture. And there are applications in security as well. And I'm using a very old example here, face recognition. This is actually a pretty mature technique where we want the machine to predict which boxes contain faces, okay? And if you have used one of the most important face application in the world, that's Facebook actually, you will see that it has those face detection modules built in. When you upload your pictures, the modules can detect the faces and even suggest whether those faces may correspond to some of your friends. And the data we have, faces, non-faces, and for Facebook, even other data that the platform has access to. And this is rather mature technique, okay? But as you can imagine, the one that Facebook needs, okay, arguably for recreation, can be very different from the one needed for security, okay, for using faces to access, for example, your smartphone, okay? Some smartphones have Face ID and so on, and the face recognition there would be for security purposes, and that requires different kinds of tuning to be successful. Other applications, including education, and in this particular education application, we may have students' records on quizzes, okay, on a math tutoring system. So on the tutoring system, there are many different kinds of questions, and students answer them. So we have some super big data about how each student answered each question. The skill to help the students learn better is really to predict whether the student would answer a question correctly on the next question or not. This helps measure whether the student have sufficient knowledge, and this also helps plan for the curriculum of the student. And how can we model that? Okay, so this is the first time we'll talk a little bit more about machine learning models, actually answering some of the questions that we had on the Slido, saying what the pattern is. One way to model this problem is to say, okay, we want to predict whether the student would answer the question correctly. Our model can be divided to two sub-goals. One is to predict the strength of the student, and the other is to understand the difficulty of the question. If the strength of the students is higher than the difficulty of the question, then the student can possibly answer correctly. And here I'm going to tell you one notation that we will use in this class, basically this square bracket, okay? And this square bracket means a Boolean operation. Okay, so if the condition inside the bracket is true, then it returns 1 for true. And if it's false, it returns 0. Okay, we will use this notation throughout this class. Okay, so if we want to predict whether the machine answers the student answers the question correctly, we can predict the strength, predict the difficulty, and done. That's our model. That's the pattern we're going to seek. So what we do is to give the machine 9 million records from 3,000 students about how they answered some of the questions, and the machine determines, or in the engineering literature, we call it reverse engineering actually, determines the strength and the difficulty automatically. Okay, try to compute, okay, with some, for example, statistics model or formula or whatever, the strength and difficulty at each timestamp, and then try to make the prediction accordingly. This particular model, this particular solution is a key part of the world champion system that our team designed, the National Taiwan University team designed in KDD Cup 2010. KDD Cup is one of the most important machine learning and data mining competition around the world. And back in 2010, NTU won a world champion. And this particular model that you see above is a key part of the system that we had at that time. And I was very fortunate to have worked with a team of super good students and other professors to get this world champion at that time. Okay, now another application, recommender systems. Some of you may use recommender systems in your daily life. For example, if you have used some music playing system, the music playing system like maybe KKBox or Spotify would recommend you the songs that you may like. And here we are using some other applications that, for example, you can think when you are watching Netflix, okay? And the data that we have are how the users may have rated some past movies. And the skill predict how a user would rate an unrated movie in the future. Okay, so you can think of the skill as predicting the user's future preferences. So we know how to recommend the best movies to the user. This is an important problem, and machine learning researchers actually started studying it back around early 2000. There was a competition held by Netflix in 2006. Some of you may have heard of it. And Netflix at that time provides 100 million ratings that 480,000 users have given to around 2,000 movies. Okay, a little bit, 20,000 movies. And the goal at that time was to get 10% improvement. Remember, machine learning needs to be measured by some sort of performance improvement. And the goal at that time was 10% improvements. And the first team that reaches the 10% improvement can get $1 million. Okay, that was the prize Netflix provided at that time. And I was a Caltech PhD student at that time. And actually, we formed a team to participate in the competition. Now, one question for you. Did I win the competition or not? Or did our team win the competition or not? Okay, and as you probably guessed, no. Okay, otherwise I don't need to teach here. But actually, our team performed pretty well in the competition and learned lots of experience there. There was a similar competition held by Yahoo in KDD Cup 2011. Okay, remember KDD Cup, the most important machine learning and data mining competition. While in Yahoo, there was a service called Yahoo Music. Okay, so the competition was on music, okay, not songs. And the data was even bigger than the one provided by Netflix. Okay, how can the machines learn our preferences, our music or movie preferences? Well, one way to do that is to say, the rating we provide to some movie actually depend on the factors of the movies. Okay, the movies may have factors like who is the leading actress, who is the leading actor, what's the type of movie, and so on. And we may have our preferences. Okay, for example, I like Julia Roberts. Okay, so that may be the part that I prefer very much. I don't like horror movies. Okay, so that may be the part that I less prefer, and so on. So if, okay, we have the movie factors on hand and we have the viewer factors on hand, then the rating can really be predicted by some sort of matching between those factors. And what the machine can do is from the known data, the known ratings, the machines can extract the hidden factors, the hidden underlying factors. For some of the factors, we may have them on hand. For some of the factors, the machines have to extract by themselves. And if we have the factors for every viewer and every movie or every item, then the machine can perform unknown rating prediction. And this is the key part of the world champion solution. Again, by National Taiwan University. Again, by our team, actually, a different team of students, but the same professors in the team. This is back in 2011. Okay, we won the competition in KDD Cup. Of course, you'll ask, okay, so then how many dollars did you win? Okay, there was a $1 million US prize by Netflix. And how about Yahoo? Well, in KDD Cup, the price was a few thousand, if I recall correctly. And again, this is still why I'm teaching here. We didn't want the $1 million, and the thousands of dollars were actually distributed to the students, not the professors here. Okay, but that's honor. And actually, back to the days when we actively participated in KDD Cup, NTU won 6 world champions within 4 years. Okay, that's a very, very extraordinary achievement by our teams. Okay, so I'm hoping that these examples motivate you that machine learning can be used in lots of different applications. Okay, now let's check the questions on Slidos now. Okay. Good. Okay. So there's one question here, and I'm going to translate it. The question is asked in Chinese. Okay, if my English is just very, very bad, okay, but I'm very willing to follow the videos for a few more times, and can I participate in this class? The short answer is yes. Okay, it may be hard, but yes, we're going to teach in English, as you can see here. But I truly believe that you can understand the materials with a few more time of watching in English. That's one thing. Okay, and one thing I mentioned in the course introduction video, but perhaps I'm going to take the opportunity to ask to tell you one more time. One purpose of teaching in English is really to encourage you not to be afraid of English. As you can see here, my English is not perfect. My English is far from perfect. Okay, if a native speaker is watching the lectures with us, I'm sorry that my English is not perfect, but it shouldn't stop us from learning English. Okay, it's just an opportunity for both of us, okay, to sharpen our English skills, okay, through observation. This is a machine learning class. I have to hint that we're doing some sort of observation here. For you, you are accumulating the observations through our course slides, through listening to me, through reading others' posts, and so on. For me, I'm accumulating observations through your feedback, through practicing, through everything, so we can improve our English skill in some sense. Okay, so that's one thing. If you really find the English teaching part too hard for you, the very first part, I think the very first 50% or 60% of the videos have their Mandarin teaching versions in the MOOCs that we provided a few years ago. And I'm going to actually point you to the related lectures. Okay, so you can try listen to me in English first, and if you really want to understand some parts in a different language, you can go to those videos. Those videos are public, and understand them in Mandarin as well. We're hoping that those additional resources can help you learn the most throughout this class. And of course, you need to spend more time on that, but we believe you can learn. Okay. And pattern, definition of the pattern. Now there's another question. If the data is very complicated, how can I know if there is pattern? Okay, usually we don't know for sure, but we can guess. we can make conjectures. We make conjectures when we build machine learning models, and we let machines do the rest. Like how we make conjectures through in the recommender system problem or in the education problem. We make conjectures, and if we have enough data, machines can try to do the rest. And if the machine is successful, it's successful. If the machine is not successful, we may realize our conjecture is not so good. We can refine our conjecture, and that's what we actually do in real-world applications. Okay. There's a question on whether you can choose this class if you have taken machine learning foundations but not machine learning techniques. We have answered that in the course introduction video. The short answer is the school policy prevents you to do that, okay? But we won't actively check. And if you have only taken machine learning foundations, you will find the very first part of the class significantly overlapping, okay? That's the good or bad part. And then it's your choice, okay? It's your choice to try to explain why you are taking overlapping classes, and it's your choice to basically pass through the school if there's a policy of not allowing that. Okay, but for us, for me, we won't actively check. Another question, well, I basically call names, okay, in this class. The short answer is no. Okay, we really don't have time or good interactive mechanism to say who attended the class, who didn't attend the class, or not in the class. We won't be able to do that. Okay, so in a sense, you can take the course in your own pace. Okay, you want to follow the live lecture, enjoy the live Slido interaction, fine. Okay, you really want to take it on your own with faster or slower rewatching of the videos, that's fine. Okay, and there's a question on whether there's a possibility to start from whatever successful machine learning model that we have, and then go back to getting some important features, okay, that we can observe in our data. And the short answer is yes. Okay, this is kind of usually called a machine learning assisted, okay, data analysis. Okay, sometimes you have data in your field that you really want to understand the underlying pattern of the data. You design the model, you let the machines extract the most significant patterns that the machine can see from the data, and then you use human to examine whether those patterns correspond to some scientific findings that you may want to explore on or not. Okay, that's definitely possible, but usually requires a deeper understanding of the machine learning models so that you can explain the patterns that you get in a more professional manner. And also, it is an active research direction now to have machine learning models that are somewhat explainable to help the domain experts. Okay, great. We have run about 50 something minutes, and for the density of this class, I believe it's best that we take a 10-minute break before we continue, and I'm going to use this time to clean up some of the Slido questions that we have answered as well, so we can be more concentrated in the next part. So let's take a 10-minute break before we continue the lecture. Thank you. Okay, welcome back with us. Okay, let's continue with our lecture before we go to the Slido questions. Okay, so now we have learned some applications of machine learning. I'm going to make it concrete by starting with one particular application as the metaphor that we will use to go into the more abstract models of learning. The application that we are going to use is on credit approval. Okay, so basically, think about you are in the bank and the bank wants to decide whether to give credit cards, okay, to a new applicant. In terms of data that we have, there can be applicant information. For example, maybe the age, the gender, the annual salary, and so on. All kinds of things that you try to fill in your application form. And the unknown pattern to be learned, okay, basically what we want the machine to decide is whether approving the credit card is good for the bank. We insist on the pattern being unknown, okay, because if we know the pattern, if we know what the best decision rule looks like, we don't need machine learning, okay. Only when it's unknown, we need machine learning, okay. So we try to guess this unknown pattern from data. Now, the notations that we will use, okay, starting with the inputs, okay. The customer application would be denoted by X, okay? And that's typical in machine learning to express the input part. And the outputs that we want, okay, whether approving the credit card is good or bad for the company will be denoted Y. Now we have, you see, several different versions of X and Y here. Let me introduce them a little bit. We are going to treat X as a vector. Okay, as you can see, I'm using bold faces to indicate X. And this bold face actually means X is a vector, because we may have multiple dimensions, multiple fields that the customer basically wrote in the application form. And for this Y, I'm not using the bold font. I'm using the original italic math font, basically. And that means it's actually a real number. Okay, those are some of the ways we're going to distinguish between vectors and real numbers in this class. I'm using some sort of more calligraphic scripts fonts here, and those are used to indicate sets. Okay, so if you are not too familiar with those set notation, it's totally fine. Okay, we're just trying to indicate that those are some possible customers, okay, some possible inputs that we're going to consider, and this is the output space, okay, the possible output space that we want the machines to consider. Now, we're going to call the unknown pattern to be learned the target function, okay, what we want the machine to learn. And this, you can imagine that it's the ideal credit approval formula, okay, the ideal formula that every bank wishes to have, okay, and it is just a function from X to Y. So basically, if we have this function, we can feed it with any new customer X, okay, and during writing, I cannot easily write bold fonts, so I'm going to use this little underline here to indicate a vector. I can feed X to this F to get what's the best, what's the ideal decision. And for data, we're going to consider the simplest kind of data that we have on hand, which is data that the bank can gather from its historical records. Okay, so let's say we have 1,000 customers and 1,000 past customers. For each customer, we know whether it's good or not to have approved the credit card. Okay, so maybe the customer did not pay back the money and so on, then it's bad to give her or him the credit card. But if the customer basically repays very regularly, then maybe it's good. So let's say the bank have 1,000 data in its database, and whether giving that customer the credit card is good or not. We call this our data sets, or sometimes we call it the training examples. Each of those, okay, this 1, 2, 3, up to 1,000 is a training example. And I'm assuming big N training examples. And here I'm using a number, let's say big N is 1,000 or something. Okay, so you have these examples in mind, and you want the machines to try to get a hypothesis. Think of the hypothesis as another function that the machines learned. Machine learned this formula, and we will use this formula for future prediction. We'll use this G, which is another function that we call the hypothesis for future prediction. Why do we use G but not F? Because F is unknown. We don't know F, but we want to get a G instead. Get a G from the data instead and use G instead. For G to be doing well, we want G to be as similar to F as possible, which is the goal here. We have data that is produced or that represents some unknown function that we have. After machine learning, we want to get a G, a hypothesis that's hopefully close to the underlying F. That's machine learning. Okay, that's our way of switching from the hand-waving application of machine learning to the mathematical definitions. And this is the learning flow, and we will refine the learning flow a bit throughout the next few lectures. But basically, we think this is the main parts that machine learning happens. We have training examples, we have a machine, main brain of machine that we call learning algorithm, and we want to get a final hypothesis. And this is hidden kind of behind the scenes. Okay, so we assume from the environment, we have gathered some data. We don't know the exact function, but we assume that the data that we have on hand is produced in some way from the function we want. What we hope to guarantee is that this unknown one, as if I haven't emphasized it enough, is close to this final hypothesis that we obtain. And the target is unknown. No programmable definition, as we mentioned, and we hope that the hypothesis is similar. But one important thing, it's similar, but possibly different. It is very normal for G to be different from F because machines are not perfect. Okay, we want to highlight this in advance because sometimes people may have the fantasy that machines are so powerful, it can do everything perfectly, ideally, and so on. But no, we're doing a pretty hard task here. We're asking the machines to infer the best hypothesis from the data, from the limited data, and therefore the best G can be not 100% the same as F. G will be different. G will be good, but not perfect. Or at least we want G to be good, but we shouldn't expect it to be perfect. Okay, that's a very important concept that we should have in mind. Okay, what does G look like? What should G look like in this particular credit approval application? Well, there are some possible G that we can think about. For example, on the application form, we may have annual salary, and we may tend to believe that people with a higher annual salary may be a better candidate in terms of giving the credit card. Or sometimes we may have some different functions. For example, we may have those functions saying, okay, if you have a significant amount of debt, we should give you credit card. because maybe you will use our credit card to pay the debt first, and then we can get more interest from you. Okay, maybe not you, okay, from the applicant, and so on. So that's another function. Or there are other functions, like maybe we are targeting towards fresh members in the job markets and so on, for whatever reason. So there can be reasonable functions. There can be other creative functions that we can think about. But anyway, if you ask the machines to think about all the possible functions by varying, for example, the factors being considered here, or maybe the threshold being decided here, there are just lots and lots and lots of opportunities. We don't know which one is good. So then we don't know. What do we do? We ask the learning algorithm to check that. So what we do here, we assume to have a very huge set of possible functions for the machines to pick, and we call this very huge set the hypothesis set. And here the hypotheses I showed you are very simple ones. This is just for illustration. In the future, you will learn much more complicated hypothesis sets. Okay, but in any case, we have a hypothesis set that the machine can decide from. Okay, it's like a set of possible candidates. And what the learning algorithm does is it picks a candidate from the hypothesis set with the hope that the picked hypothesis, the G that's picked from the hypothesis set, is close to F. Hypothesis set can contain good or bad or wild hypothesis. Okay, basically whatever we think is a sort of reasonable one for the machines to select from. Okay, we will discuss later about the cons and pros to have a big hypothesis set versus small hypothesis set and so on. Okay, but hypothesis set doesn't have to be containing all the best hypotheses. Okay, it can contain all the possible hypotheses for the machine to choose from. And it's up to the algorithm to pick the best one. I'm using quote on best here, okay, because it will take us several lectures to really understand what we mean by best, okay? But just think intuitively for now. The best one means the one that can match the data that we have on hand, right? The two inputs to a learning algorithm, the data, the hypothesis. What does the learning algorithm do? Try to match the data with the hypothesis as much as possible. Okay, and that's the intuition we have in mind, but we will justify later on how or whether this intuition is true. And we call the learning algorithm, along with the hypothesis that we're considering, the learning model. Okay, so in this learning model, the hypothesis part contains all the possible hypotheses or all the possible pattern that we want the machine to explore. And the learning algorithm contains how to explore those patterns, how to truly identify some patterns are the ones that we want to pick the final hypothesis. And the practical definition of machine learning can therefore be put this way. We're going to use the data to compute, to pick a hypothesis G from H that approximates, okay, that tries to be as close as possible to the target, the unknown target F. That's the practical definition of machine learning. Let's see if we have any questions on Slido. Okay, let's see. Okay, the top question, can we only write our homework in English? Short answer is no, and please check the course introduction slides. We have answers there. A comment is that my English is basically sounds good to your ears and so on. Okay, thank you so much. Actually, I don't consider that. I don't consider my English to be super good and so on. But inside the question, do I or did I do any special practice for my English? When I was younger, kind of yes. Okay, when I was studying in the US, actually, I spent lots of time practicing not just my English speaking, but basically presentation. Okay, and that's a very important part of my PhD study. And after I started teaching in school and also becoming chief data scientist at a company and so on, I keep cherishing every opportunity to use English. And one thing is that I believe good pronunciation comes from good listening. Okay, so if you want to practice your English, I highly recommend you to watch, for example, movies or TV series in English, and that actually helps improving my learning ability, my listening ability, as well as my speaking ability. Okay, will there be a break time? Yes, we had a break time. And about the final project, allow me about a week or two later before we give you the details, because I need to discuss with the teaching assistants on our setting this time. Okay, auditing, and please check the course introduction video. We have answers there. What's the difference between the course and machine learning technique and foundations? Please check the introduction video. We have answers there. Do we have to get the textbook? Please check the introduction. The short answer is no. Okay, but we encourage you to try to find some way to read it, and the course introduction have more details on how to different ways of getting the textbook. And also, if you want, if the book is not affordable to you, let me know and we can try to do something. And this is an interesting question. Can we use machine learning to give English caption to the course videos? The short answer is yes. Or we can use this opportunity to revisit the 3 criteria. Is there a pattern in the translation task or the voice recognition task? Yes. Okay, so we are speaking towards meaning in terms of words and writing, that's the pattern. Or we are, if we're doing translating from Chinese to English, there's a pattern, and so on. Is it easily programmable? Arguably not. Okay, because okay, it's just hard. Okay, to program every grammar, every phonetic pronunciation, and everything. And are there data? Okay, yes, there are tons of data. Of course, whether you have data of sufficient quality and quantity, that's questionable. And also, whether you have enough computational power, that's questionable. That's one thing we didn't mention in the 3 criteria. Okay, but at least for the basic checks, the task is suitable for machine learning. It can be hard for machine learning, but it's suitable. Okay, another interesting question here is how much data is enough? The short answer is it's hard to know. Okay, generally we say the more the better, and the higher quality the better, and so on. Okay, so it really depends on the basically complexity of the problem that you're trying to learn. General rule: for more complicated patterns, for more complicated learning problems, you need more data to cover enough of the variations that the machine would encounter. That's the rule of thumb. And in the future lectures, we will introduce some theory of machine learning, and that can give us some hint, okay, about how much data is enough from a practical point of view. What is reverse engineering in the education example? Okay, very good question. And reverse engineering actually means when you have a black box and you don't know what the black box is doing, but you try to test the black box in various ways and trying to guess, make conjectures, okay, on what the internal components of the black box are and how to assemble them to achieve the same purpose as the black box. Okay, that's what people generally call reverse engineering. And we are hinting that machine learning is doing something similar. The black box is the unknown function. Okay, now we know the terminology, the unknown f that we want to approximate. And what the machine does is to use data and the hypothesis, okay, to do this reverse engineering to compute, for example, the internal parameters of the hypothesis set, okay, to pick the hypothesis such that the final outcome, the G that we get, is close to F or as close to F as possible. Okay, great. Now let's go back to the lecture. Now, when we teach here, now that we know the basic definitions of machine learning, people ask, how does it connect to other fields, other related fields that we may have heard of? Okay, and here we're providing some of our understanding or some of my personal opinion about the connections. Actually, you'll realize that different people may have different opinions about the connections, and what I'm presenting here reflects my view. We know machine learning is to use data to compute a hypothesis that approximates the target function. One very related field is called data mining. Actually, if you recall, KDD Cup is a competition in the machine learning and data mining field. What data mining tries to do is to use the huge data to find property that is interesting. Okay, find within the data what's an interesting property. And if the interesting property is the same as the hypothesis that approximates the target, okay, for example, in some data, maybe we have a very clear goal, and what we want to do is to see whether this data can achieve this particular prediction goal. That's the interesting task, that's the interesting property. Then machine learning and data mining are usually just the same. This is what KDD Cup does anyway. Okay, so KDD Cup, there's a goal, a very clear measure, computable performance measure, and so on. That's the most interesting property that we want to find within that data. And in this sense, machine learning and data mining are the same. If the interesting property is related to the hypothesis, okay, the hypothesis that machine learning wants to find, then data mining can help machine learning, and vice versa. What do we mean? Well, for example, if we use some data mining techniques, for example, in data mining, there's a technique called frequently pattern mining. It tries to identify some patterns that coexist in the data. It finds a pattern. The pattern may not necessarily need to be used for prediction. It can be used for human analysis and so on. Okay, but if you run the frequent pattern mining algorithm on your data, get some frequent patterns, then it can help you design better machine learning models. That's how data mining helps machine learning. For machine learning, one student asked, can we use machine learning to get patterns within the data? And I say, yes, it's machine learning assisted data analysis. And that's basically machine learning helping data analysis or data mining. Traditional data mining also focuses on efficient computation in large databases, okay? Because if you roll back to 30 years ago or something, the computation power is not that good and so on. So when people started to do data mining, they actually need to design very efficient algorithms within databases to achieve the goal. And traditional data mining wants to do that. Modern data mining also deal with computational issues, for example, distributed computing in the cloud and so on. Okay, so when we talk about data mining, we often have a thought in mind that we're using some huge data. In reality, it's very, very, very difficult to distinguish machine learning and data mining. I call myself a machine learning researcher. I also call myself a data mining researcher, or I go to conferences in both machine learning and data mining. Okay, although there are different conferences which are more specialized in data mining or machine learning respectively, but it's really hard to distinguish them. Usually, data mining is considered more application-oriented, while machine learning can have a wider algorithmic or theoretical spectrum. Okay, that's another difference when people talk about these terms. But in general, we don't try to distinguish them very clearly. Machine learning and statistics. Okay, machine learning uses data to compute the hypothesis that approximates the target. Statistics also starts from data. But what it tries to do is to make inference about an unknown process. Okay. There's something we don't know. For example, the proportion of small fishes, okay, in a lake or something. And we design techniques to gather the data and then use the data to make inference. Okay, like through basically in the lake example, okay, maybe we gather the data and then we do some counting, calculate some numbers, and we use those to make the inference. Or you can think about, for example, the polls we're running in the beginning of this lecture, or the voting, okay, that we do to elect some candidates and so on. Those are some of the processes that we try to have to infer what's the underlying unknown number that we're interested in. Okay, so G, if we look at this, we can think of the hypothesis G that we want as an inference outcome, while F is the something unknown we want to infer. Okay, we want F, we don't know F, we use data to get G instead as our inference. In this sense, statistics can be used to achieve machine learning. Actually, as you will see later, many important machine learning techniques rooted from statistics. But traditional statistics is a field of applied mathematics, and therefore what people focused on are provable results with math assumptions. Okay, so basically set some assumptions and try to derive some math results in terms of what can be achieved. So you can think of statistics as getting as being closer to the theoretical side of machine learning, okay, with some more focus on math assumptions and traditionally less focus on computation. Data mining, the other end, okay, focus more on computation and big data and so on, but less, or arguably less, okay, on mathematical assumptions. Both statistics and data mining can help machine learning. Okay, if you think about bringing computation with mathematics properly in the machine learning process, and there are many useful tools from statistics for machine learning. And again, for me personally, I don't like to distinguish whether this is statistics, that is machine learning, and so on. It is not that crystal clear which part is statistics, which is machine learning. And actually, I think good machine learning should embrace every possible tool from every possible subject. Okay, so traditional data mining tool, statistics tool, or even more pure mathematical tool or control tool or whatever. Modern machine learning should have all these tools within our system to truly help improve our application. That's my personal opinion. Now, another important term, artificial intelligence. Machine learning uses data to compute G that approximates F. Now we're very familiar with that. Artificial intelligence try to use machines to compute something that shows intelligent behavior. Intelligent behavior is a very broad term, okay, and very traditionally people have very high hopes for artificial intelligence, wanting the machines to do various different things, okay, that can demonstrate some sort of intelligent behavior. And being able to approximate an unknown function well, or being able to achieve some decent performance in this task is something that shows intelligent behavior. Right? We're essentially doing some sort of prediction or inference, as statisticians say, or getting interesting patterns. That's somewhat intelligent. And in this sense, machine learning can be used to realize artificial intelligence. It's not the only way to realize artificial intelligence. Okay, there are different ways that we will talk about in some later lectures, but machine learning is a possible direction, and actually a very popular direction. For example, in terms of chess playing, traditional AI, there's one direction, okay, analyzing the game tree, okay, so basically trying to simulate some possible moves and getting whether the moves are good or bad to make a decision on whether to play it or not. Machine learning for artificial intelligence goes through another route of learning from board data. If we have lots and lots of board data, maybe simulated or from real human playing or whatever, if the machines can analyze them properly, then machines can know what the best move possibly is. And guess what? Both the game tree and learning from board data are part of the AlphaGo system that you saw in the news, okay, that beat actual human beings in terms of Go. Okay. So this actually shows traditional AI possibilities, machine learning possibilities, both very important to reach a decent AI system. We will talk more about this later. And therefore, we should be modest here. Machine learning is important for artificial intelligence, but it's just one possible way, not the only way. And following, okay, our discussion that skill or measurable performance of G approximating F is actually similar to an intelligent behavior that we want to achieve. Another way of looking at machine learning is it stands between data and artificial intelligence. It shows us a data-driven way to achieve artificial intelligence. If you think about artificial intelligence as the dish that we want to serve the customers, then machine learning are the tools and steps to transform the ingredients to the delicious dish. Okay? And the ingredients are the data. Machine learning starts from data, and you may want lots of different ingredients, and that's the big data term that you may have heard in the past years. Okay, again, as if I haven't said it enough, machine learning is not the only tools, but a popular family of tools that people use nowadays to achieve artificial intelligence, and that's arguably why machine learning is a hot topic nowadays. Okay, questions? Okay, one particular question: would this class focus on specific machine learning techniques like deep learning or support vector machine, or while we cover the more general concepts only? You can check the syllabus. Okay, actually we have syllabus on the course information page, and the short answer is we will cover both. Okay, in the beginning we will give you more general concepts, before we use those concepts to get into deeper techniques, okay, that are used in actual machine learning systems nowadays. Okay. So there's a comment that so this semester there you won't see my name calling machine. Generally not. Okay, it's just too hard and inefficient to do so in an online setting. What is hypothesis actually meaning? Okay, hypothesis means a conjecture. Okay, a guess. Okay, you are guessing something. And for here, we are using a hypothesis function. So we are using the function to represent a possibility that we want the machines to choose from. Okay, so initially, we have many hypotheses, 10,000 of them, 20,000 of them, or maybe infinite number of them. And we want the machines to pick one hypothesis from them as the candidate. Okay, like in the credit approval example, the candidate formula that we will actually use, that we will call as the outcome of machine learning from our data. What if we change the scale or the amount of training examples? Will the final hypothesis change, or will the final hypothesis keep the same? And that's a good question. And for typical machine learning algorithms, when they choose a hypothesis from the hypothesis set, they choose it according to the data. Okay, so if you have more data, you have fewer data, you have different data, then the hypothesis, the chosen G, is likely going to be different. Okay, and F is the same. Okay, but F is unknown. Okay, so we don't really care whether F is the same or not. Okay, but F, only God knows, it stays there. But G, that's what your learning algorithm chooses, depends on the data that you have. Okay, great. I think we are in a place where we should perhaps take another 10 minutes of break. Okay, by the way, I won't take break strictly at the clock or something. Okay, we will take breaks generally depending on the pace of the lectures that we're taking and so on. Okay, so I usually we'll take 2 breaks, okay, in between the lectures and so on, but I'll try to choose the time for 2 breaks so we keep a reasonable pace of the class. Let's take a break now for another 10 minutes before we continue with the rest of the lectures today. Thank you. Okay, welcome back. And to begin, I actually checked the some more Slido questions, and we'll start by answering some of them before we move on to the next part. Do we have to have a hypothesis set? Okay, are there any algorithms that can find out totally unexpected hypotheses not in the set? Well, in a sense, even in the situation that you describe, there's a hypothesis set, okay, because the mere the mere action that your machine is going to output the hypothesis, okay, means it belongs to some set. Okay, so think about the hypothesis set as all the possible outputs from your machine learning algorithm. Okay, so for us humans, okay, we may consider it to be totally unexpected and so on. But for the machines, okay, the hypothesis is in the hypothesis set to begin with. That's why the machine can return that value. Okay, so that's kind of a philosophical point of view. Okay, when we build the machine learning algorithm, when we build the machine learning model, we put in the hypothesis set every hypothesis that the machine can output. Okay, so in that sense, being expected or unexpected, okay, being good or bad is the machine's judgment. Okay, but for us, we can be rather general. Okay, in terms of the hypothesis. Okay, so then even in that case, okay, you can say there's a hypothesis. We will describe later on whether it's good or bad to include all possible functions in the world in your hypothesis set. Okay, this is a tricky thing. Okay, basically, when we talk about hypothesis set, we think, okay, maybe we include a finite number of them, we include a parameterized set of functions and so on. Okay, but what if we include every possible hypothesis, every possible one in the world into the hypothesis set? This is also similar to what you described in this question because, okay, in that sense, the machine can output anything. Is it good or not? Well, for this, we really need to discuss later about the theory behind machine learning and whether it's good or not. Okay, and there's an interesting question on whether linear regression is a machine learning method. We'll have this discussion. Actually allow me to postpone it a little bit later. When we teach you teach you linear regression, we will actually teach you linear regression later in the lectures. But let me put a short answer. Linear regression is something that's rooted from statistics. Okay, so it can be viewed as a machine learning tool, as a machine learning model, and it doesn't matter whether it's simple or not. Okay, but for our perspective, we need to find or we need to understand, okay, whether the linear regression improves some measure of interest or whether linear regression produces a hypothesis that's similar enough to the underlying F. And that's something we will talk about. How do you measure the 10% improvement in the Netflix example? What are the parameters? Okay, in the Netflix case, the organizer, which is Netflix, provided some data, actually some hidden data that can be used to evaluate how accurate your model predicts for users on some unseen movies. In this particular question, how do we interpret that G and F can be different, but G is good? Okay, so basically, that's something we'll talk about later. Okay, so we mentioned that machine learning produces G. We want G to be close to F, but G will be different from F. Okay, then how do we put this into practical procedures? Okay, that's something we will talk about. How do we evaluate machine learning and so on? But for now, let's assume that we have test environments. Okay, for example, in the computational finance case, you push your machine learned hypothesis into actual investment and see whether the investment gain is good or not. Okay, that's how we determine whether G is close to F or not. Okay. Are there any problems that could be solved by machine learning but are too hard to do so? Kind of yes. Okay, and usually the hardness lies in two parts. One, whether you have enough data. Okay, so there are things that, in principle, you can use machine learning to solve, but maybe you don't have enough data. Or maybe if you don't have enough computation. Okay, so back maybe in 20 years or 30 years ago, people may not always believe that many of the computer vision problems that we see nowadays are solvable by machine learning, because at that time they don't have enough data, they don't have enough computation. Okay, but after gathering more and more data, after having more powerful computation, things could become easier in terms of using machine learning to solve the problem. Okay, so that's some of the questions that I want to answer, also still following the priorities that you guys provided in voting. If you are interested in some of the questions, it's really important to upvote them so I can try to answer them as much as possible. And for some of the more logistics problem, I'll answer them offline. And please visit the course introduction video because many of those questions are answered in that video as well. Okay, let's go back to the next part of the lecture. Now, we have learned the basic learning flow. Here we have training examples that go to a learning algorithm which chooses from a hypothesis set to get a final hypothesis that we want to be close to the unknown target function. Now, a question that many of you asked, and it's very natural to ask, is what's a hypothesis? Okay, or how do we choose a hypothesis and so on? Those are very big questions. We'll possibly need many more lectures to answer, but we can make things more concrete by telling you one hypothesis set that we will study in the very beginning of this class. And let's start from the hypothesis that we may have in mind. Okay, one way that we can think about evaluating the customer, evaluating whether to provide the customer credit card or not, is to use a weighted score. Okay, so in a sense, we are scoring each of our customers. And if the score is above a threshold, we approve the credit card. And if the threshold is below the threshold, then we deny the credit card. Okay, so that's the basic thoughts that we have in mind. And this score can come from multiple factors that we observe from the customer's application. These multiple factors are called the features, typically called the features. Remember, we represented the input by x, which is a vector, and this vector we're going to assume it to be d-dimensional. Okay, each dimension is a number. For example, in the customer here, we could assume it to be 4-dimensional, and each dimension, the first dimension says 23, a number. The second dimension says, 1 million. Okay, maybe we represent by 1. A third dimension says, 0.5. The fourth dimension says 200,000. Okay, maybe we represent by 200, and so on. And each of these features can help us evaluate, whether we should approve the credit or not. We can compute a weighted score from them. Okay, the weight may represent the importance of each feature that we observe here, and also basically whether the feature is positively correlated or negatively correlated to approving the credit or not. Okay, so for example, maybe we can have one particular hypothesis saying, let's approve credit if we use this way to compute the feature. 23 multiplied by 0.8, 1 multiplied by 30, 0.5 multiplied by 1126, 200 multiplied by 0.01. Okay, we sum this to get a score and test whether the score passes a threshold or not. So by changing each of the orange numbers here, each of the W here, we change the way we evaluate. And also, we can change the scores as well. So changing each W, changing each threshold changes, okay, a possible function that we can use for credit approval. So each of those is considered a hypothesis. Okay, in the hypothesis, okay, we have this little W and this threshold here. Those are the changeable parts. Okay, that corresponds to our H1 function. In mathematical form, what it does, provide a sum, okay, a weighted sum, that's our score, minus the threshold, deciding whether it's positive or negative. And that's the outputs that we demand. So our output space, that's the spatial Y here, contains two possibilities, positive one or negative one. Two possibilities that we want our hypothesis to output. Okay, so in terms of sign, positive number, that means the score is higher than the threshold, we output positive. Negative number, score is less than the threshold, we output negative. There's a minor technical detail that the score can be exactly the same as the threshold. So this equal threshold case, okay, that we will ignore for now. It almost always never happens in practical machine learning, and we'll explain later on how to deal with this. But now let's keep things simple. We calculate a score which would be greater than or less than a threshold. We compute the sign of the difference. That's our hypothesis. Varying different W and different threshold gives us a different hypothesis. And this particular hypothesis would be called a perceptron. And our hypothesis set just contains all possible perceptrons that we can think of. All possible, meaning you can vary W to any number you want. You can vary the threshold to any number you want. You get a different H, you put that H in your hypothesis set. Okay, one thing before we move on to the discussion, okay, because in the discussion above, we have two kinds of variables. One being the weights, okay, that we use to combine the features. The other being the threshold we use to make the comparisons. That looks a little bit too complicated. So we use some mathematical trick to simplify it. What we do is we call the threshold a special name. What it does is we have some special number that we name x0, and then our intention to minus subtract the threshold can be represented by another variable that we name w0. So w0 corresponds to the negative threshold. With this mathematical trick, what can we do? We can change our submission here by a simple trick that's, okay, we are starting with from I from 1 to D. Now we have another dimension from 0. Computer science people, loops should start from 0, right? So all we need to do is to start from 0 here. Then we can use a simple summation instead of writing so many other characters to represent the formula we want. And that's basically the notation we're going to use. We're going to assume we insert a dummy variable to our vector x. So that's our original x. We have x1, we have x2, blah, 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 xd. we are injecting a dummy variable x0 here, a special one, to make our x a little bit taller. Okay, and what's the result we get? Well, if we want to make x taller, we also need to make our w vector originally containing w1, w2, w3, blah, 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 wd. We also want to make it taller. We add w0, which represents negative threshold. With the slight change of notation, making x taller, making the w, which is scattered in a vector form, taller, we can write things even simpler as an inner product between w and x. Of course, both in the taller version. Okay, summation, multiply and doing summation is just an inner product. And I'm going to represent inner product with this little t here. That's the transpose of a vector. So if you recall, we have a vector x, the tall vector x. And if we write w should be something like this. If we want to do an inner product, what we can do is to make w lie down, that's transpose, okay, and then multiply, doing a matrix product with x, okay, sorry, that should be black x, to get the result. Okay, so I'm using this transpose, okay, to reflect that we're doing inner products. So we simplify the notation with not just vectors, but taller vectors, okay, for both taller x and taller w. In our class, if we don't mention otherwise, we will use the taller version throughout. Okay, that is, we always assume that we add this little dummy x0 into x before the operation. Okay, now with this mathematical introduction, what does the perceptron look like? Let's see things here. So each hypothesis, okay, let's see how each hypothesis looks like in 2D. In 2D, we have all the points, okay, every point in 2D being our little x. X contains x1, x2. Right, every point, okay, let's assume that it has a coordinate that's x1, x2. And then we are trying on this point to decide with respect to some parameter w, w0, w1, w2, whether the result is positive or not. Let's imagine there's one line here. And this particular line is of normal vector w1, w2. Okay, if you have trouble understanding why a line can be represented by its normal vector, please check linear algebra. Okay, that's a very simple concept within the linear algebra. But basically, let's look at this. Okay, if there's this line and the equation of this line is w1 x1 plus w2 x2 plus w0 equals 0. Okay, a line needs to come with an equation. And this is the equation of line. On the line, every point x satisfies w0 plus w1 x1 plus w2 x2 equals 0. Then on one side of the line, and I'm drawing with positive here, and I'm drawing with blue here, is the positive side. On this side, all the points have their value evaluated with w0 plus w1 x1 plus w2 x2 to be positive. Okay, so this line is what we call a classifier. It classifies one side as positive and the other side as negative. So every hypothesis can actually be visualized as a line on this 2D space. The perceptrons in the 2D space are just the lines. And you are saying, okay, I understand that W1, W2 is the normal vector of the line. If you're Mandarin speaking, 法向量，这条线的法向量。I understand it's the normal vector of the line, but where is W0? Well, W0 determines the intersect of the line. Okay, so basically, 截距. Okay, if that's your high school math. Okay, W0 determines the intersect. So if you change W0, you'll be shifting the line, okay, across the plane in some sense. If you change W1 or W2, you'll be rotating the line because you are changing the slope. 斜率, you're changing the slope. So each hypothesis corresponds to a line. Each of the original data that you see corresponds to a point, a labeled point. So in machine learning, what actually happens is you give the machine some points. Circle the positive points, cross the negative points. You want the machine to do from all the possible lines on this 2D plane, pick a line as your G. And you want this G to be good. Then you want, and this particular G says that this is positive and this is negative. Okay, so you want to find such a G. You have infinitely many different G to consider. That's the infinite number of W, W1, W2, and also W0 that you can change. And you want the machine to find a good line. So in a visualized way, that's what we do in the credit card approval example. If our customers can be described with 2 features only, we provide the machine with data, the positive data, the circle, the negative data, the cross, and we want the machines to infer a line as the G. Okay, and hopefully this line does well on the data that we have seen and on the data that we will see later. Okay, so those are perceptrons. We also call it linear classifiers, okay, because it can be visualized as a line in a 2D space. Of course, generally we are going to deal with spaces that are much higher dimensional than the 2D space, okay? But basically, that visualization should hopefully give you a strong concept on what we're doing now. And we call it binary classifiers because we only have 2 outputs from this linear classifier, positive or negative, okay, on different sides of the line. Questions? Okay. Some people are somehow surprised by the Chinese. Okay, I actually I'll use English to describe in most of the cases, but sometimes I'll inject some of the Chinese terms if I believe that it's significantly easier to help our Mandarin-speaking students understand the context while not being too interfering to other students. Okay. Okay, the question here is whether the threshold is determined by ourselves or whether machine determines it in a better way. Now, we will talk in the next part about how to learn W. Okay, how to learn W meaning how do the machine pick the best line. The best line includes W1, W2, W3, W4 up to WD, and W0. Remember now we have included W0 as negative of the threshold, or we have included threshold as a special W. And therefore, everything machine picks. W1, W2, W3 up to WT, WD, and W0. Machine picks. We are going to talk about a learning algorithm that chooses both the hypothesis weights, the W1 up to WD, and the threshold. Okay, Much. Okay, great. Let's move on to the next part because I really want to finish the next part. We possibly will not always close the lecture with everything we prepare to teach. That's fine. Okay, we will just follow our nature pace and so on. Okay, we don't need to be rushed into too many things. Okay, but in general, I will have some minimum pace in mind that I want to keep. Okay. Okay, so our goal: designing an algorithm that selects a hypothesis from the hypothesis set. H, all possible perceptrons, or as we know now, all possible lines in 2D. And what's the best G? We want G to be close to F. Okay, but this is hard because we don't really know F. Okay, for all we know, F can be any funny shape that God has in mind. But if we want G to be close to F, maybe we can go back and think about whether G is close to F on the data that we have observed. Okay, and we have assumed that our data is generated by F. Okay, and by generating, I'm assuming a kind of a noiseless case where each example has its desired outcome from the ideal target function. So if we want G to be close to F on D, the evaluation of G on X should be close to the Y, or sometimes we call the label. So applying G on X should get us Y as much as possible. And the difficulty is that our hypothesis set is of infinite size. Remember, we have infinite number of lines on in the 2D space. So how do we pick one? Okay, you cannot afford to enumerate every possible line by a for loop and so on. You need to design an efficient algorithm. Actually, almost every machine learning algorithm that you will learn about is an efficient algorithm to search within infinite number of hypotheses. So our idea is as follows. We have examples, we have lines. Okay, I'm not going to mix them. Okay, we have examples, we have lines. If our line is not perfect yet, we try to transform, we try to tune the line, we try to use rotation and shifting to make our line better. So this is what we're going to do. Starting from the examples we observe. Okay, remember those circle and cross are the examples that we have observed. And keeping a current line on hand, we are going to try to rotate the lines towards making the line perfect. Perfect meaning for every example, the output of the line is the same as the label we want. Or, shortly speaking, we want to find this line, which predicts this side to be positive and the other side to be negative. We want to be able to rotate our line in some way until we find this green, very beautiful line that's clearly right on every example that we have observed. And we'll start from some hypothesis on hand. Okay, and remember in our hypothesis sets, every hypothesis, every edge, let me use a darker color here. Every edge that we have can be represented by the W. The W, W0, W1, W2, the W vector inside. So therefore, we can focus on how to update W. We're choosing a hypothesis. Equivalently, to choose a good hypothesis, we can choose a good vector W. So we start from a vector W, and then we try to update the vector W to some better vector W that suits our need. Now I'm going to call the initial vector w, w0. Do not confuse this initial w, w vector 0 with the w0 within a w vector. Okay, within a w vector, we have w0, and we say that's a scalar, that's a real number, w0, that's in every w. But now I'm highlighting that I am focusing on a vector, a whole vector. And this 0, if you like, is just trying to indexing the number of changes that I have encountered. Or if you think this is really too confusing, you can imagine this vector w0 to be w parenthesis 0, or whatever way that you're comfortable with. Okay, so basically highlighting that it is another loop variable that we're using. Then the loop vector is on the whole, the loop index is on the whole vector rather than indexing on a particular scalar component. Okay, those are different. Okay, starting from a w0, and I'm going to illustrate how we can correct the mistake. If we have a line that's not perfect, then there must be some example that the line does wrong. Wrong meaning it's on the wrong side. So if it's a circle, wrong side meaning it's on the pink side, not the blue side. So what do we do? If we have something like this, we are trying to rotate the line closer to that wrong circle. If we rotate the line closer to that wrong circle, we can correct this in a bit, so that the line may be better in the next iteration. So this is what we're going to do. If the line is not perfect, there must be an example where the line makes mistakes. And we're going to call this particular example xn, yn. Okay, there's nt, okay, which means we're counting the number of iteration with t here. So the notation is a little bit complicated, but if it's too hard for you, just call it bug. Okay, let's find a buggy example. Let's find an example that the current line does wrong. What does this bug satisfy? The current line, we call it WT, vector WT. When we use vector WT and feed it with the input part of the bug and take the sign, that's just evaluating HT of X. Right? At that iteration, we have a hypothesis on hand. We feed it with the inputs. We feed it to the formula of the hypothesis. We get a result. And the result, to our dismay, is wrong. Okay, it's wrong. It's a bug. Okay, it's not that particular example is not on the correct side. What do we do? Let's do rotation. Remember, if that example is a circle, it's a circle on the wrong side. What we want to do is to get our line. Remember, this is the normal vector of the line. So your line would look something like this, orthogonal to the normal vector. You want to rotate this line because the circle is here. You want to rotate this line clockwise to make it closer to the circle, to be something more like this. Then originally the blue side of the line is here. Now after the rotation, the blue side of the line is here, which likely makes this particular example correct. So here we are rotating clockwise. One way to represent that we're rotating clockwise is we are changing the particular W by the vector indicated with our X. With our X NT. That achieves the rotation we want. On the other hand, this is a symmetric case that's left to your exercise. If X is wrong, but it's not a circle, it's a cross, then we want to rotate the line far away from that cross. So we want to rotate, in this case, counterclockwise. That is, we need W2 minus X. Combining them together, the update equation that we want to use to achieve this rotation is W, the original W, plus Y, which is positive or negative 1, depending on whether the wrong example is a circle or a cross, and then the example. So the bug example is used in this way. Okay, saying if you find a bug, check whether the bug is a circle or a cross. Okay, and then perform the updates accordingly. This would rotate the line. I'm using rotating the line to illustrate this, so you may think I'm just updating W1 and W2. But the beauty of linear algebra is that we can do the same as W0, so there will be some shift effects as well in the two-dimensional space, or rotating in the three-dimensional space to our wish. Okay, so basically, when I talk about the updating here, I'm using the vector notation, and this particular vector, d plus 1 dimensional, this particular vector, d plus 1 dimensional, we're updating all the weights and W0. Okay, the intersect or the negative threshold that we're going to use. We're updating the whole vector. That's the algorithm we're going to use. It's called a perceptron learning algorithm, developed very, very long ago, 30 years something ago. And that can achieve, okay, well, as we will show later, the goal of finding a perfect line, if we happen to have that. Okay, so this is what we're going to do. We're going to run this algorithm, keep finding a bug, finding a mistake, and then updating the line, updating the W corresponding to the line until there are no mistakes. When there are no mistakes, we know we find a perfect line. There's a W there, this last W at some iteration, and this last W will be returned as our hypothesis, returned as what we call WPLA, where PLA stands for the perceptron learning algorithm. Okay, so again, visualizing what we're doing, this is the 2D space. We started with some data circle and some data cross. We started with some line, okay, some temporary line. For example, this one that's not perfect. We find a bug, okay, of that line. Okay, so basically a mistake made by that line. And using this bug, we rotate the line in some sense to get a new line. A new line that I'm going to illustrate this way. We are going to run this for a few iterations, or luckily maybe in one iteration, we just find the line that's perfectly separating the blue and the red on all the examples that we have observed, and we're going to return this line as our WPLA or our G. Okay, everyone getting what we're doing? Let's go check some results. This is, I like to call it an interesting algorithm. In English, it's called a false confessed is half reject. In Mandarin Chinese, it's 知错能改. You observe where the mistake is, 知错, I mean knowing where your mistake is, and 能改 actually means you can change. Okay, so we change, we correct the mistake by some update rule that we just introduced you. Of course, I haven't proven to you whether this update rule is correct or not. I'm just giving you the intuition that it's rotating towards the direction that we want it to be. How does the algorithm work? Okay, before we give you some visualization of the results, let's put a little bit more detail on the practical implementation. We start from some initial vector, and let's say initial vector can be the 0 vector. Actually, for the 0 vector, remember our special way of treating the sign. The 0 vector would always be incorrect with respect to the sign, right? Because it returns 0, not positive 1, not negative 1. So we would always get into an update. One way to implement this is that, okay, in every iteration, we try to find the next mistake with some order. For example, we can just say, let's check the first example, second example, third example, and so on, until we have a full cycle of not encountering any mistake. That must mean every example is correct. This is called the cyclic implementation of perceptron learning algorithm, and you possibly will need it in your homework. That's why we illustrate it here. You just follow one by one, examples one by one, check whether there's a mistake. If not, then continue. If there's a mistake, then you correct the mistake and move on. So that's the cyclic implementation. Let's see how this implementation works. Initially, let's say we feed the machines with this circle and cross. And remember, we say initially we start with the 0 vector, so it must be wrong. On some example, we identify that particular example. That's the X we're going to take. And I'm assuming this middle point is the origin. Okay, so this purple vector here is the vector of X. This is wrong. We need to correct. How do we correct? We sum our W, which is the 0 vector, with this X, okay, which is the purple vector here. That actually means after summing, we should get a line something like this, perpendicular, orthogonal to the new weight vector that we are going to get. So this is what you're going to see after I change the figure. You see a new line formed, and this particular new line is represented by a purple vector that's exactly the same as our X, because we add X to this new weight vector. Okay, so you see a separation of this new line here represented by our current W. Is the current W correct? No, it's not perfect yet. So we need to find a bug. And this algorithm finds this particular bug here. This circle is on the wrong side. Wrong side. So what do? We need to do correction. How do we do correction? Current W, correction direction represented by X. We sum them, get a new weight vector. So the new line that we are going to get after the correction should be something like this. Update. Did we get a new line? Yes, we get a new line. And of course, there are many lines here, so I'm not actually drawing the line, but there's a fuzzy boundary here that you can see representing the separation between circle and cross. Is this new line perfect? No, let's find a bug somewhere. The bug is here. Okay, so what do? We need to do correction. This correction, we have the current weight vector, we have the update vector, opposite direction because it's a negative example. And we merge those vectors, we get a new W, and this new W should rotate our line to somewhere like this. So rotate again. Well, so you're seeing that this particular algorithm is rotating back and forth, back and forth, back and forth. Okay, but it's getting maybe better and better. Initially, it may overshoot. Okay, but it's getting better and better. So now we're familiar with the process. Current line here, bug here, correction here, new weight vector here, corrected to this line, and done. Okay, so let's continue the process and correction, 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 and correction. Okay, so after several corrections, and this circle may look on the boundary, but it's just because of the plotting resolution issue. Actually, it's correct in the blue side. Okay, so then you see that after several corrections, we finally identify a line represented by WPLA, and this WPLA is three-dimensional: W2, W1, W0. Okay, that tells us what's the best way to separate the data, to classify the data. And this particular algorithm works with like 20 lines, and it's going to be part of your homework 1. Yay! Okay, but it may look kind of magical to you. We haven't proven to you anything about this algorithm, and you have an intuition that it's doing some sort of efficient search by going back and forth with the rotation and so on. And after some iterations, it identifies the best line that we can see, the best in some sense, okay, with respect to the data. There's a technical note here, okay. Although I'm saying we are updating with three-dimensional vectors, W2, W1, W0. Remember I said W1 and W corresponds to rotation, and W0 corresponds to shifting. So if I actually implement this algorithm in three-dimensional space and then project it to a two-dimensional space, you will actually see the two-dimensional line shifting, okay, shifting in different areas of the figure. And this makes it a little bit hard to visually illustrate what we're doing in terms of vector summation and so on. So what I decided to do is to make the shifting part visually as minor as possible. So you only observed the rotation while there's shifting. The shifting is so minor that you cannot observe with your naked eye. How do I do that? I made xi, okay, xi meaning the features that we have in the other components, much bigger than x0. So when we update W, we update with big X values. When we update with W0, we update with small X values. As a consequence, rotation would look much more significant than shifting. Okay, that's how I do this demo. I actually ran the algorithm with 3D updates, with updating 3 variables. But because the updates on W0 is so minor, you won't be able to see it in this visual demo. Okay, so that's Perceptron learning algorithm, and we see that it works. Okay, it corrects the mistakes that we have observed on the dataset until there are no mistakes. There are several issues that are still there. First, in terms of algorithm, there are lots of people from computer science in our class. You may think, okay, the halting problem is one issue. How do I make sure that this algorithm will not run indefinitely? Okay, how can I make sure that it would terminate without any mistake? We have introduced you the Cyclic version, and there are other versions of Perceptron learning algorithm you can think about, because basically you just need to find a mistake and correct, a mistake and correct. You can use different ways of finding the mistake in your implementation. And do all those implementations halt? Or maybe some of the implementations hold and some don't. We don't know yet, or at least we haven't proved it yet. And in terms of learning, which is our main problem, well, can we guarantee that G is close to F? And there are two parts. One is whether G is close to F inside D, inside our dataset. If it holds, maybe yes, because inside our dataset, if the algorithm really hot, we get a perfect line, and that's cool. But how about outside D? Or how about when the algorithm doesn't hot? We don't know, and those are the topics we're going to study in the very first part of this class. But I'm going to give you some hint, and we'll start proving this in the next class. Basically, we're going to show that after enough corrections, any perceptron learning algorithm variants would halt. Any implementation that you choose to use will halt with a perfect line under some assumptions that we're going to introduce. Okay, great. Let's see if we have any more questions. Questions. Okay. Okay, one question, whether it's possible to not meet the criteria of no more mistakes. This is similar to the halting question that we just discussed in the previous slide. And short answer, yes, it is possible that the algorithm does not terminate. And we will discuss the condition that makes it terminate and the cases that make it run forever in some future, I actually just in the next lecture, after we showed you the detailed proof about the running complexity of this particular algorithm. Okay. Okay, here's one particular question for the previous part of the lectures. How to differ AI from traditional programming? Is computer in some games count as AI? In a sense, actually any attempt to make computer smarter, okay, can be called AI. And therefore, you can also say every programming attempt is doing some sort of artificial intelligence. Okay, it's just I think the answer is not black and white. Okay, whether this counts as AI and that doesn't count as AI. Programming can be viewed as a direction that makes computers smarter, and in that sense, you achieve a certain level of AI. Okay, but maybe if you're just programming with 10 lines or something, your AI is arguably not very deep, or possibly not very deep. Okay. By the way, there's a request to focus more on lecture-related questions and so on. And yes, okay, we will try to do that. Actually, I'm doing that by leveraging your votes and so on. While if your question don't get answered in live, don't worry. I'll answer every question offline, okay, in a document form that you can read later. Okay. And there's one question on whether the origin is at the center of the demo that we just showed you. Yes, okay, so I put the origin point in the center. So basically connecting the origin to any example is the vector, the x vector that we want to use. Okay. What's the difference between the training dataset and hypothesis set? Okay, the training datasets are data. Okay, so basically we have the input, our desired output, and so on. That's reflecting the original observation that we have in mind. While the hypothesis set is sort of like in the algorithm brain. Okay, the algorithm decides, okay, like when you are deciding what to have for lunch, okay, we're almost lunchtime here. You have a bunch of candidates in your mind that you want to choose from. Okay, so Hypothesis the computers, okay, internal brain, data, external knowledge, okay, that we provide to the computers to do machine learning. How to know the correctness of our prediction? Can we prove it or not? Okay, that's a good question, and we are going to discuss this in the theoretical part of machine learning about maybe 3 or 4 weeks later. Okay, so basically we are going to discuss how do we measure G to be close to F, okay, which actually means whether G is sufficiently correct or not. Okay, let me go to the top here to see if there are other questions, other top questions, okay, that we haven't answered. There are questions to the TAs that we will answer in a document form. Actually, I need to check with the TAs anyway, okay? And questions about final project we'll answer later. And what does W0 affect? Remember, W0 affects the threshold. So for example, if you set the threshold to be super high, you should have what? You should have almost all your predictions to be negative, right? Okay, so if W0 is very negative, then you are likely to predict almost the whole plan as negative. So you are shifting the line in some sense, okay? I'm going to illustrate with a figure here. Okay, so this is a particular line, and if I change the W0 part of this line to be more and more negative, I can get a new line somewhere like this, where this whole part would be pink, okay, because it's more negative. So if I make W0 more negative, I'm shifting the line. The line is of the same slope, the same W1 and W2, which decides the slope, but with a different W0 that tells me, okay, I only have other parts being blue, but a bigger part being pink, okay, being the red, the negative part. Okay, and there's a question on why W0 changes very little in the illustrative example that we provided. And I'm saying here, I'm using a trick to set x0, the 0th component, to be super small, xi, the other component, to be super big. So when we do the update, remember when we do the update, what do we do? W vector plus or minus the x vector. So if some components of the vector is big, it changes big. If for some components that are small, it changes small. So this makes W0 changes small. Other Wi changes big. Okay, so W0, the 0th component, the scalar, the real value, changes small. Other Wi changes big. So visually, you only see the part that's changed big, not the parts that change small. Okay, we are running out of time, so please allow me to answer all the other Slido questions through document form. Okay, so basically, I'll prepare an offline document to answer all those questions. Thank you very much for participating in our first ever lecture, online lecture that's taught in English today. And if you have any feedback about how we can make the course better, please provide them on the Slido as well. I will check those comments and I will try to think about whether we can incorporate them in future lectures. Thank you so much. That's the end of the lecture today. Thank you.